All right, I kind of rushed through this is really number 2, part B. So part A, we figured out that this object would be 0.009 parsecs away, all right? And then they ask us, what would its apparent magnitude be? So we got to figure out what its absolute magnitude would be. And so it's absolute, and they tell us that it's 10 times the luminosity of the sun. So the formula, the absolute magnitude would equal the absolute magnitude of the sun, which is, sometimes we use 5 just to simplify things, but I'm going to use the exact amount, 4.8 minus 2.5 times the log of the luminosity of the object divided by the luminosity of the sun. So this one happens to be 10 times. So the log of 10, of course, is 1. So this is just 4.8 minus 2.5. So that's 2.3. All right. Anyhow, if that's the absolute magnitude of this object, and we know the object is 0.009 parsecs away, we put that in for D, right, 0.009. Take the logarithm of both sides so we get everything here in the exponent into the, out of the exponent. And so it turns out that, multiply both sides by 5, you get 5 times the log of this 0.009 is equal to the apparent magnitude, which is what we're solving for, minus the absolute magnitude, which is this number right here. We just calculated that, plus 5. And then, so ultimately when you do it, which I already answered in the last video, it's going to equal 5 times the log of 0.009 minus 2.7, right? Because that's when you have, 5, positive 5 minus 2.3, that's where you get the 2.7. And so you got to bring that to the other side, so it's negative. And so that turns out to be negative 12.9, which is roughly the apparent magnitude of the full moon. All right, so just to give you an idea how bright this thing would be. All right, let's do problem number 3. All right, it says, number 3 says, what is the greatest distance at which an RR Lyra star of absolute magnitude 0 can be seen by a telescope capable of detecting objects as faint as 20th magnitude? In other words, the apparent magnitude is 20, the absolute magnitude is 0. All right, and so we're going to solve this problem. So let's switch to this, and of course this is our problem. So the distance in parsecs is going to equal 10, and remember the apparent magnitude was 20. The absolute magnitude was 0, so this is, I'll just put it in for good measure, is minus 0 plus 5, right? And then that whole thing divided by 5. All right, so this turns out to be 10 to the, what power? Let's see, do I have it? 10 to the 5th. 10 to the 5th power. And that would be, 10 to the 5th is, of course, 100,000. So this thing would, with the telescope can see to a magnitude of 20, and it has an absolute magnitude of I think it's an RR Lyra variable star. Then this object would be, the maximum would be 100,000 parsecs away. All right, so that or actually let's write it slightly differently, and in fact we're going to use this with when we talk about galaxies a lot. This is 100. Since this is 1,000 right here, we'll call it 100 kiloparsecs. All right, that's very typical galactic distances, or even sometimes we get megaparsecs as well. All right, let's do number 4. All right, so number 4, and now keep in mind what we just did in number 3. Number 4 says the typical Cepheid variable is 100 times brighter than the RR Lyra. Remember, we used an RR Lyra for number 3, so we're going to compare these two. How much further away than an RR Lyra star can a Cepheid variable be used as a distance tool? All right, so this is number 4. All right, so here's how we're going to do number 4. So it turns out if something is 100 times brighter, you might recall that is 5 orders of magnitude. So basically, if we compare this to problem number 3, where the absolute magnitude was 0, if the Cepheid variable is 100 times brighter, that means that we can simply change the absolute magnitude from 0 to -5. All right, everybody understand that? It's from 0 to -5 because they give us this information, because it's 100 times brighter. That's anytime, that's the whole idea of 5 steps in magnitude. Anyhow, so what we do is, we use this distance equation, and so the distance, recall the last, well, we'll do that afterwards. So this is going to be 20 minus a -5, right? Because it's 100 times brighter, so it's minus a -5 plus 5, and then divided by 5. So this is really turns out to be 10 to the 20 minus a -5 would be 25 plus 5 would be 30, and then 30 divided by 5 would be 10 to the 6th. If you recall, that of course is 1 million. All right, so 1 million. All right, let's see, did I write enough zeros? One more 0. 1 million parsecs. Or another way of saying that is 1 megaparsec. And recall, in problem number 3, okay, so just to compare this to number 3. In number 3, we found the distance was 100 kiloparsecs, right? 100 kiloparsecs. All right. So what's happened is by increasing the brightness by a factor of 100, we can see further by a factor of 10, right? Because 10, that's supposed to be a 10. So 10 times 100 kiloparsecs gives us a megaparsec, right? So that answers the question. It increases the distance scale by a factor of 10. All right, so let's look at number 5. And number 5, by the way, we actually did a lab on this. The lab about proper motion. So we'll take a look at this. All right, so here's number 5. It says calculate the proper motion in arc seconds per year of a globular cluster with a transverse velocity relative to the sun of 200 kilometers per second. All right, and a distance of 3 kiloparsecs. Do you think this motion is measurable? All right, so let's turn to the problem. All right, and so this is what we're going to use. So the transverse velocity v, so that's what v sub t is equal to. This is actually already turned. This constant changes everything into arc seconds, or it makes it so that mu is in arc seconds. Mu is the proper motion in arc seconds per year, and in this particular thing, p is the parallax, but remember 1 over p is the distance. So we can rearrange this equation and solve for the distance. Now we already know the distance. They give us the distance as 3 kiloparsecs, and we want to find out what mu is, and they give us the transverse velocity as 200 kilometers per second. All right, so let's work on this problem. All right, so again, here's the equation. The transverse velocity is equal to this constant times mu, which is the proper motion, times the distance. All right, and so rearranging this equation, mu is equal to the transverse velocity divided by this constant divided by the distance. Right, so they gave us the velocity. It's in kilometers per second, as it should be. There's the constant, and then the one thing is you got to remember that 3 kiloparsecs is 3,000 parsecs, and so this turns out to equal. Let's see, what does it equal? It equals 0.014 arc seconds, and I'll just use the double hash marks, per year, right? And yeah, so and this is definitely observable. This is something that we can measure in our telescopes. All right, and we could measure that even 100 years ago with not too much difficulty. Let's do number 7. All right, so actually, let me turn back to this and we can read number 7. Number 7 says, all right, so remember, that's the last one we're doing for this chapter. Using the data presented in this figure, estimate the distance from the galactic center at which matter takes 100 million years and then 500 million years to complete one orbit. All right, so we have to look at we have to draw a picture and understand what's going on. All right, so the key thing here is we look at this figure. What we can do with that figure is we can, it shows the distance in kiloparsecs versus on the x-axis it's the distance, and then on the y-axis it is the velocities in kilometers, in hundreds of kilometers per second. All right, so what we're going to do is, let's take a look at this. It's of course 1 parsec, so we need some conversions. 1 parsec is 3.1 times 10 to the 13th kilometers. But more importantly for this particular problem, 1 kiloparsec, so you multiply both sides by 10 to the 3rd, and so 1 kiloparsec is 3.1 times 10 to the 16th kilometers. Anyhow, this is the velocity of anything that's moving in a circle, right? And let's reason this out. Okay, so the circumference of a circle is actually related to its radius. Okay, so it turns out that the circumference divided by twice the radius, so 2 times the radius, is this quantity we know as pi, right? So in other words, the circumference is the distance that you're traveling, so the circumference, c, is equal to 2 pi times the radius. All right, so, and if you know the period, the time to go around, and that's exactly what they gave us, this is basically distance divided by time. The period for part A, this is supposed to be part A, that's supposed to be an A. For part A is 100 million years. We need to change that into seconds, so it's, let's see, the value I got is like 3.16, I rounded it to 2, but 3.16 times 10 to the 15th. And then the second part, they say, okay, what about 500 million years? So in other words, if it takes 500 million years to go once around the galaxy, this would be the time in seconds. We need the times to be in seconds. Oops, so I messed that up a little bit. That's not years here. Sorry about that. This should be in seconds. All right, so here, let's erase that. And we'll switch back. And so this is actually, here, let me get my, this is seconds. All right, so 500 million years is 1.58 times 10 to the 16th seconds, and 100 million years is 3.16 times 10 to the 15th. All right, so now we can actually do these problems. All right, so I'm going to tell you what I did when I looked at these, when I looked at the chart that they want us to look at. All right, so here we go. So both of these velocities should turn out to be about 250 kilometers per second. So here's what I did. Looking at that chart, it turns out that at 4 kiloparsecs, so this is 4 kiloparsecs in kilometers, divided by, 100 million years in seconds, turns out to be 250. All right, and then I did the same thing, and I found that at 20 kiloparsecs, so that this would be the distance, 20 times